Hey guys, so welcome to the very first General Chemistry 1 video lecture. Um, so there will be a series of video lectures every week. Normally I'll do one video per section of a chapter. So we're going to begin with a little bit of a review of Chemistry 139. So in chapter 1, we're just going to be covering essential ideas of general chemistry. And this is, stuff that you saw in Chemistry 139 presented a lot quicker and in a little bit more detail. And in particular, what I would say is that the problems that you're going to be asked to solve are a bit more complex than what you were seeing in Chemistry 139. So you don't want to be underestimating the nature of the problems that you're going to be asked to solve, and you want to allow plenty of time to work through the work that you've been given. So video lecture is not the most exciting thing in the world to do. You don't really get to see my personality. I don't get to see your personality. There's not really the chance for any back and forth discussion. I feel kind of stupid cracking jokes when it's like, just my dog is sitting in the room beside me. It's kind of just a little clunky, so please bear with me. I hate listening to the sound of my recorded voice, so I'm not going to go back and edit these too much. They're going to be done in one take, and so they might have a little bit of me and ahhing, they might have a little bit of me making some errors, but, it's just going to kind of be the true me in a sense, and, I hope it's not too awful for you. I'm going to do my best to keep it interesting. Okay, so here we go. So the first thing is to kind of try and put chemistry in some context, explain what it's all about and where it fits into our larger understanding of the world. So we're going to begin with defining what we mean by chemistry. And, I always start this with a sort of like a bit of a lighthearted take. When you ask the average person in the street, what is chemistry, at least when I do, it generally tends to be a negative response. You're going to get something like, oh, it was the most boring class I ever had to take. Oh, it was so hard. I did so terrible. I got an awful grade in it. It was really difficult. I was confused the entire time. A lot of people will come back with this one. I hated it. It was awful. I never want to do it again. And for some people, they're like, I had to do it like 2 or 3 times. It was a real struggle. And I guess, how I feel about this is that you might be feeling one or more of these things during, this course. And I hope that that's not the case for too many of you. I'm going to do my best to make sure that, that doesn't happen. But what I would encourage you is please don't kind of give up, please kind of try and at least I'm going to try and help you get through it, and so that you can move on and get going with your careers, right? So, it's probably a little bit too much to think that every class that you take will be exciting. Every class you take, you will easily grasp the material. Every class you take will be, with a fabulously wonderful professor. You're going to get a few stinkers during your college career. And, I hope it's not my class, but, if you do, if it does happen to be my class, I'd just encourage you to kind of hang in there and, let me know that it's not going well, and let me know how I might make it a little bit better for you. And we'll try and, do what we can to improve things so that you can get through it, move on, be successful, and get going with your life. Okay, so on a more serious note, chemistry can be defined as the scientific study of matter, the properties of that matter, and its transformations, and sometimes that's referred to as changes of the matter. Okay, so there's 4 terms there. Let's kind of have a look at each of them. So chemistry is part of science, right? So we need to kind of see where it fits into science and define what we mean by science. So chemistry, because it's concerned with matter, and a lot of the universe, a lot of the important aspects of the universe can only be explained if you understand how matter is behaving. For this reason, chemistry is often referred to the central science, because it kind of fits in with a lot of other scientific disciplines. It's important in a lot of other scientific disciplines, and it's why for most STEM majors, in fact, almost all STEM majors have to take general chemistry because it's kind of like a key concept, chemistry, physics, mathematics, sort of like foundations of science. So you'll hear sometimes people will describe chemistry as being the central science for this reason. Okay, so we've kind of got the concept of where chemistry fits within science, but we haven't actually defined what science is itself. So back in the old days when we wanted to know what a word was, we wouldn't Google it. Believe it or not, what we would do is we would look it up in the dictionary. So when you do that, you get something like this. The dictionary defines science as being knowledge or a system of knowledge covering general truths or the operation of general laws, especially as obtained and tested through the scientific method. And you might recognize some of those words from Chemistry 139. So we talked about the scientific method, we talked about scientific laws, we talked about experiments and testing things. But there's a lot in this description of science. My initial response to this was, what? So it needs a little bit of unpacking. So let's kind of like take it a little slower, and this is my version of trying to figure out what this sentence means. So I'm going to say that science is an approach to the study of the universe, right? It's one way of studying the universe. And it's probably important to recognize that there are other ways of studying the universe, philosophy, mathematics, and then there are like ways that traditional sciences societies studied the universe that might not be defined as science, or might not have all of the elements of what we think of as modern science. But they are valid in in many cases, but we're talking about sort of the Western concept of science, right? So it's not that there aren't other ways of studying the universe. Science is just one of them, and it's going to be the focus of this class. So in science, an assumption is made that the universe obeys laws of natural origin. So the laws that we're talking about are not like societal laws. They're not things that we made up. They're not things that we created. They're things that just exist, right? They're just like there. They are of what we call natural origin. We didn't create them. We can't destroy them, and we can't change them. Whereas with a societal law, if you don't like it, you can vote out your congressman, or you can appeal the law, and you can work to get it changed. Laws of natural origin are just there. You're just kind of stuck with them, right? So we're going to assume that the universe, there's some kind of like underlying series of laws which it is following. And those laws just exist, and we're just trying to figure out what they are and how they work. So that's what scientists do. They are trying to identify these natural laws and understand how they operate. And the mechanism through which they're going to do that is this thing called the scientific method, which is really an elaborate way of saying trial and error. Okay, so scientific method at its core is a sort of a method of trial and error. We're going to propose explanations. We're going to test those explanations. If they're wrong, we'll go back and revise them. So the scientific method is a generalized procedure. It's not something that's kind of like, it's just an idea in the back of the mind of scientists. It's sort of like a general way of proceeding, but it's not like a formal standard operating procedure. So that's kind of an important thing to recognize, is that it's just sort of like a way of thinking rather than a very strict series of rules. So in the scientific method, we'll typically begin with making what we call observations, right? And these are just kind of like looking at the natural world and seeing what is there. We might kind of like poke at things and see what the response is, these observations might mean, like looking at things that have been written down. It doesn't have to be, like observing the natural world. But what you're going to get is you're going to get a large collection of observations, and hopefully this could take some time. You'll try and summarize what the key sort of trends are in this large collection of observations. And that's what we mean by a scientific law. A scientific law is a summary of the key aspects of a large number of observations. Now, when you're making observations, we often like to do them under what we call, if possible, it's not always possible, under controlled conditions, so that we know the conditions under which the observations are made. Now, when you're looking at something like the operation of something large like a planet, or perhaps a very large collection of people, it's difficult to have controlled conditions, and that complicates things. So once you've got kind of like a large number of observations and you've kind of made note of what the trends are within those observations, then you want to kind of like try and explain why you are seeing the things that you are seeing. And your initial attempts at doing this are referred to as being a hypothesis, or there might be more than one hypothesis for a set of observations. The key thing about science is we always want to be able to test whatever explanations that we're coming up with. So scientific hypotheses have to be testable. And that's kind of different from some other kinds of hypotheses. In philosophy or mathematics, it's legitimate to propose hypotheses that may not be testable. But in science, our hypotheses have to be testable. We have to be able to perform experiments or make further observations in order to check if our explanation is correct. So a hypothesis, a scientific hypothesis, is a testable explanation that's tentative. It's not well tested, right? It's tentative. We're quite open to the idea that this could need modification. And so when we test our hypothesis, the data that we collect, the results from our observations and experiments, if they disagree with this hypothesis, then we will revise our hypothesis. And we kind of go around this loop here, around and around and around until we have a robust and sturdy hypothesis that seems to work for every case that we can think of. Now, when we're collecting data to test our experiments, it's really a good idea if we can, limit things to only one thing changing at a time. Now, so that we don't kind of complicate the matter. That can be very difficult. It's hard to study, whether, when not more than one thing is happening at a time. Like most likely, rain is going to be accompanied by the wind blowing and stuff like that. So, it's not always easy to isolate just one variable at a time. So if you kind of keep collecting data that supports your hypothesis, there gets to a point where your hypothesis, by sort of general consensus of the scientific community, gets promoted in status and it becomes a model or theory. And this is kind of like, a arbitrary kind of point, right? Now, good theories explain the results of lots of experiments and are also able to predict related phenomena. So they can predict the results well of experiments that we are yet to conduct. Of course, we never stop testing our theories or our models. We always kind of keep trying to, break them, because that's how we kind of improve them. We keep testing them. We keep seeing whether the predictions of these theories are indeed correct. And if they're not, then we'll go back and we'll revise our theory. So a theory is kind of like a well-tested, generally accepted hypothesis, right? So really, that's the only difference between a hypothesis and a theory is that a hypothesis is considered to be kind of tentative, and a theory is considered to be well tested. Now, good models, are simple. They have an elegance around them. So scientists will often strive to create models that avoid unnecessary complexity. There's a famous quote, I think it's an Einstein quote, that sort of says, you don't really understand something until you can explain it to your grandmother. So that's the kind of, sort of idea that scientists have in the back of their mind. If it's horribly complex, we probably don't understand it well. So we're talking about, where does chemistry fit into the realm of science, and it's important to recognize that chemists work across three major domains. Chemists study things that are macroscopic, that you can see with your eyes. And this can be objects as large as galaxies or clusters of galaxies. This could be something like an iceberg here. It could be something like a person. We study things that you can kind of see and touch and are part of our everyday experience. Chemists also study things on the microscopic domain. That is, we study things like subatomic particles, we study atoms, we study molecules, we study microorganisms, proteins, DNA, viruses, things that are too small to see without the aid of instrumentation. And then some chemists, and this will include you, they're not looking at objects that exist in the physical world at all. They're dealing entirely with symbolism. And this could be math, the famous Schrödinger equation. It could be, it could be using atomic and molecular symbolism. These kinds of things here. So, and some chemists, they just pen and paper working with math. Other chemists, like computational chemists, they just work with symbols on the computer all the time. Most chemists do a little bit of each of these three things, but the domain of chemistry kind of spans the galactic to the, entirely kind of in your head. So that's important to keep in mind, and sometimes you will be asked to classify things as belonging to either the macroscopic, microscopic, or symbolic domain. So you should be kind of aware of what those terms mean. Okay, so that brings us to the end of our first section. Hang in there, only a couple more to go for chapter 1.